I understand.
Okay, so yesterday we went over number 1. Now, if I drew this, when I drew this yesterday, let me draw the picture. Hopefully I gave you yesterday. Whoa, that's a long arrow. So we have something like that. If I draw another arrow, that is a fat arrow right there. All right.
Those look different.
They are different. So I drew this, but the idea was that I labeled this A, B, C. And I use arrows here because I kind of want to get the idea of vectors here. So once I labeled the A, B, and C, yesterday what we did is we just found the distance using the three-dimensional distance formula. Yes, Connor?
Are you doing number 1 or 12?
I'm looking at number 1 right now. So yesterday, as a repeat, what we did yesterday, and it's on the other video that you can look on online, is that we found the distances from A to B using the distance formula and the points. So we found out the distance from A to B here, and we use, again, three-dimensional distance formula, and we found out, I believe, if I remember correctly, that this was square root 59.
B was.
The distance from A to B.
Oh.
And then what we did is we said, okay, what about from...
That's square root 70.
D to C.
Okay, that was square root 70?
Yeah.
Okay, so let's go that this was root 70. Now this isn't definitely not the scale here, because I think we got root 70 here, and we got root 59 here. Not to scale. But what we ended up figuring out was that the hypotenuse here, the AC, was root 129. And because that checks in Pythagorean theorem, because root 70 squared plus root 59 squared, that does equal root 129 squared.
Because the square roots cancel out.
Correct. So that was right. It checked. We're good. So number 12 here is a slightly different question. Okay, it's asking about the vectors. Now, if we actually look at these vectors, now I'm not going to use those arrows because they're too big. I just don't like them. So let's go here. If I try to draw these vectors and make them perpendicular, we'll go here and here. Okay, so we'll call this vector 5, negative 3, 6. And then this one down here will be 3, 7, 1. Now if we look at those two vectors, those were the coordinate points A and C in the previous problem. But those are the vectors going from B. So if I go from B to A, that is the vector going from 0, 0, 0 to 5, negative 3, 6. And then the vector BC going that direction, vector BC is 3, 7, 1, because you're going from 0, 0, 0 to 3, 7, 1. That makes sense? So here's a shortcut. And we've looked at the shortcut before. Let me see if I can make this work. Give me a little bit more room here. Does this work? Let's try that. There we go. Okay, so, uh-oh. Don't want to do that.
I think you zoomed out a little.
I wanted to zoom out a touch.
Is it recording your voice?
Yes, Paul's recording my voice.
Well, because you keep answering Connor, but you said it wouldn't hear it.
So, here, if I look at these two vectors again, and I wanted to zoom out so I can look at these vectors.
Oh, you zoomed out.
5, negative 3, 6. And 3, 7, 1. There is a shortcut to figure out if those two vectors are perpendiculars. Remember those two vectors. Clarice.
Dot product.
Dot product. Thank you. So we can do the dot product with those two vectors. What is the dot product? Can you remember that?
Don't you add or vertically or
Cl-
subtract?
Close.
Multiply?
Multiply. So the dot product is multiplication. The dot product is what you would do is you multiply each component here. 5 times 3, 15. Negative 3 times 7, negative 21. 6 times 1, 6. And when I add these products together, what do I get? 0. Exactly. So that's 0. If you get a dot product of 0, then that means that they are perpendicular. So the vectors are perpendicular with a dot product of 0. Do you see how that process might be a little bit easier than what we did previously with all the distances? Yeah? Okay. So any questions on that? Yes?
Do you have to show it like on the test? Do you have to draw it out?
I would say on the test, no, you don't have to draw it out. It might help you to get the understanding, but you can't really see that three-dimensionally anyways. So I would say as long as you have the vectors and you show the dot products, you're probably okay. Okay? Now, of course, on a test, it wouldn't be maybe this easy. Okay, so I want to do a problem now that would be more like a test type question. So any questions on this one before I move on? Yes?
If it wasn't a three-dimensional vector, could we still use dot product?
Yes, you can. Good question. So Cassie, Sassy Cassie, asked that if it were a two-dimensional vector, would it still work? Yes. We did this a little bit earlier. The difference was if we have, say, vector, we'll call it mn, and we have that vector is, we like to use these types of things, so 3, 4. Okay, and then we have another vector, OP, and that vector is negative 4, 3. We've proved that they're parallel by finding, perpendicular, by finding the slopes first, and then the slope, showing that the slopes are opposite reciprocals. But if you use a dot product quickly, 3 times negative 4 is negative 12. 4 times 3 is 12. That adds to 0. They're perpendicular. We're done. So here is definitely more of a test type of question for this Friday. If we're going from, well, we have 3 points now. Notice we don't see anything with vectors. We see 3 points, similar to problem 1. And we want to show that that angle FHS is a right angle. How can we use vectors? Morgan?
Use vectors, I think. Wouldn't you go from like F to H and then F to S and H to S?
Okay, so yes, we can make vectors going from the points, right? Now where's, if and again, I don't want to draw this completely, but if I did draw this, where is the right angle going to be?
At 8.
At H, right? So if we draw this two-dimensionally, and I just have, this is F, this is H, this is S, and I drew some arrows for vectors to show that they're vectors here.
Why wouldn't you connect the third side?
Because we don't need to now. Because we're going to use dot product, right?
Yeah.
And we're going to use vectors. Joe?
Could you still use dot product if you're just solving the Pythagorean theorem instead of using the vectors?
You could just solve this with the Pythagorean theorem, but I believe that doing the vectors would be quicker. Yes?
Alright.
So if you did the vector from H to F and then H to S and you multiply the dot product of those two.
Exactly, Madison. So when you're going from H to F, let's find the vector HF. So I'm actually going to go ahead and use that notation. Here's vector HF. So I want a vector HF. So I'm going from H to F. If I'm going from H here to F there, what would my x coordinate be?
4.
4. My x component would be 4. What would my y component be? Negative 3. Be careful because you're going from 3 to 0, so it should be a negative 3. And then from negative 4 to negative 2.
2.
2. So that is our vector HF, which I had right there. So let's do the vector now HS. What would my components be of that vector?
It would be 3.
3. What else, Connor?
3 to 11 and 8.
8. And the last component?
That'd be 2.
6, because you're going from negative 4 to
Oh.
positive 2. So that would be 6.
I accidentally wrote something that made it look like a negative.
Why, if it was,
Yes.
if it was 2 to negative 4, it'd be negative 6.
If it were 2 to negative 4, it would be negative 6. And I'm going to address that issue in a second. Yes.
So from 3 to 0, how come it's negative 3?
Because if you move from 3 to 0, you're going minus 3 to get there. So once we have our vectors, we can go ahead and dot product. 4 times 3, 12. Negative 3 times 8, negative 24. 2 times 6, 12. Add them together, 0. We're done. That means that these two vectors are perpendicular because the dot product equals 0. Joe.
So if you were to use the Pythagorean theorem instead of the dot product, would you just add the z parts of the coordinates into the distance formula?
Yeah, you could add the z coordinates into the distance formula. That would work if you're going to use Pythagorean theorem. Paul.
Why are perpendicular lines right angles?
That's just the definition of what perpendicular lines are. Is if they're perpendicular, that means they make a right angle. Alexa.
Okay, but you said something about doing like ask yourself to do that.
No, so yeah, here's a question. If I would have, and let's see if it's possible for me to erase this. Yes, it is. Okay. Let's say erase these. In the picture here, would it make a difference if I would go from F to H? Would that make it not perpendicular? No. You're just flipping the sign. So actually, what would change in my vector right here?
Would it be negative 4, 3, negative 2?
Yes, it would be negative 4, 3, negative 2.
So you get the same answer.
You get the same answer. So let's say for some reason we use vector FH instead, which Connor just said was negative 4, 3, and negative 2. And I still use HS. Do you see how now the dot product is going to change like the actual products, but when I add them up, is it making any difference? No, we get negative 12, 24, and negative 12 again. That adds to 0. So we're still okay regardless of which direction we go with our vector. Yes?
Do we do anything with like F to S or S to S?
Nope. You don't need to do anything with that last side. That's why I think this is probably quicker than using Pythagorean theorem and distance formula in 3 dimensions, is because you don't need to find that third side at all now.